Welcome to 23rd session of day 3 of Wadla 3.0 on advances in deep learning session. So today we have Dr. Anish Chand and his honors work team V. Sagar, S. Naidu, and G. Eswara. So today he is going to talk about recent advances in ML analysis of hand movements using SEMG signals. So before his lecture, so I'm just going to introduce him. So Anish C, born in India, received the BTech degree in Electronics and Communication Engineering from Nagarjuna University, India in 2002. The MSc in Engineering from the Chalmers University, Sweden in 2006, and the PhD in Electrical Engineering from the Mississippi State University, Mississippi State MS in 2010. From July 2010 to January 2012, he was a Mississippi State as a postdoctoral associate. From February 2012 to January 2015, he was a postdoctoral associate in the Department of Engineering and Aviation Science at University of Maryland, Eastern Shore. From March 2015 to July 2017, he was a faculty at the ECE Department of VR Siddharth Engineering College, Vijayawada, India. From July 2017 to August 2021, he was an assistant professor at IIIT Sri City, Chittoor. He is currently an associate professor at IIIT Sri City. His current research interests are application of statistical signal processing and pattern recognition. He is an active member of IEEE and the three of its society. He has received Graduate Student of the Year Award for outstanding research from both the Mississippi State University and Centers and Institute and Geosystem Research Institute at MSU for the year 2010. He has 16 journals published and 30 conference proceedings. So welcome Dr. Anish Chand and his team. So now session is over to you.
So can the audience hear us?
Audience, can you confirm whether are you audible? Yes.
Okay, thank you. So thank you for the introduction, sir. As started the introduction, so we'll be talking about recent work in machine learning analysis on human activities, especially movements, using surface EMG signals. So this work is done at our biosignals lab in Medicine City. Mainly this work is done by our honors students, Sagar, Surya, and Ishwar. So since the inception of our lab, we have published so far 9 conference proceedings. And today we'll be talking about the conference papers 2 and 3. And as a journals, we have 4 publications so far. And the numbers 2 and 3 have been presented in the previous edition of Wadla. And another workshop was done related to statistical data analysis and modeling. So, and the journal paper 1 will be presenting in the next workshop. So, yeah, so the contents for today, we'll start with the background and motivation, especially about the work being done at our lab and the overview of the different types of human activities that we are interested in. And we will present 2 case studies. So the contents for the case studies are given here. So the same contents are followed for both the students. So let us look at the background and motivation. So our main focus at the biosignals lab is looking at these 4 different areas. Basically, looking at the intersection of these different areas. First one is human movements. Anything like activities of daily living, or just normal human movements, or hand gestures, or sports activities, strength training. Any of these things can be classified as human movements. They can be very simple movements or very complex movements. So the goal is, how do we really understand them? How do we really quantify them? So one approach is to look at their videos or look at their motion data But here at the biosignals lab, we look at the intrinsic biosignals, means the electrical activity in the muscles that actually generate this human movement. And then we use the tools such as signal processing and machine learning to extract information from these signals. So signal processing means traditionally we use either statistical analysis in time domain, or we can look at frequency analysis in the frequency domain, for example, using Fourier transform. Or we can also look at the recent advances in signal processing, such as wavelet-based analysis, where we look at both the time domain and scale domain simultaneously from the data. And then finally, we can use machine learning to make models that can make decisions from the signals. That means, for example, a signal corresponding to an activity can be really invert that problem. Given a signal, can we identify the source activity? Or can we segment the signals into rest and action? Or can we segment the signals into fatigue and non-fatigue signals? And so on. So we can make decisions of classification of those signals using machine learning tools. So that is the main focus of our work at the University lab. So let's look at some examples. In terms of human activities, there can be very simple activities such as grasping an object in different styles, palmar grasp, lateral grasp, or it can be simple activities such as pushing or opening a door, pulling a door, and so on. Or there can be repetitive activities such as writing or typing, where there is a repetition of particular pattern of activity. Or there could be a little bit more complex activities, still very, and there are no rapid movements like opening a tab, closing a tab, or any such similar activities. One important aspect of these activities is that there are no sudden movements. But if you think about activities such as strength training or sports activities, in many cases where there's always a possibility that we need sudden movements or dynamic movements of human the legs or arms. So there's a possibility of either dynamic movements or static movements in these kind of activities. For example, in strength training as well, if you think about activities such as lifting a dumbbell, or bench press, or shoulder press, any of these activities, the motion is more or less static. It means there are no sudden movements of human muscle. But if you think about activities such as running, where you are running on a treadmill or any of the athletic activities, then there is definitely a dynamic movement. Similarly in sports, right? For example, if you are doing something like a fast bowling or playing a aggressive cricket shot or doing it any service, then you definitely need a lot of coordination, but also dynamic movement of your limbs. So how do we really achieve that? And how do we really quantify all these things? Intuitively, for example, in sports, these people, for example, coaches or trainers, they understand the difference between a quality player and a beginner player or a very new person. But how do we really objectively identify these things? So these are the different kind of questions we look into. So why do we really do this? What are the practical uses or applications? So if you think about these human activities, and we are trying to quantify them using biosignals, and we are also planning to look at other kinds of data representing these activities, for example, motion data or video data and so on. But what is the practical application? What are the different areas in which we can use them? So we are interested in the 4 areas mentioned in blue, like sports science, rehab, robotics, and fitness training. So in sports science, as I said, what is the possible application? We are able to quantify the activity. We can actually understand what are the groups of muscles that are most responsible for any particular sequence of actions. For example, let us say something like a straight rep or a cover rep. What are the sequence of muscles that need to be activated, and at what time? We can look at both the temporal aspects and also the energy aspects. We can really understand what is the cause for really high quality performance. And then for beginners, we can definitely prescribe what are the actions required and what are the training strategies required to improve the output. So improve the activity performance from the example perspective of a coach. So then in rehabilitation and robotics, one practical application is, especially if you're looking at activities of daily living, they can be used as a metric for understanding the progress in rehab. For example, these are different kinds of activities. If they're able to do on their own without any support from a second person or any, for example, robotic system, that means they have progressed very well in the rehab process. But if they need regular support from a therapist, that means there needs to be improvement, right? So this can be used as this is generally used as a metric for understanding and monitoring the progress in rehabilitation. Another application is we can design systems in which we use the signals as inputs and convert them into a particular activity. And then that particular activity, for example, we are trying to move an object with your hand, and the person, say, is disabled or partially disabled, then we can use something like a wearable robot, exoskeleton, or a prosthetic if it is completely disabled. So these devices can be programmed dynamically to achieve a particular target. So instead of pre-programming them using servo motors, we can actually drive the motors with the output from the this machine learning system, so that we can achieve the required activity, that is particular movement, and also the amount of force. So, and then in fitness training, there are several applications. One simple application is looking at the fatigue. For example, when somebody is doing strength training, everybody has a limitation, right? So some people can do up to 13, depending on the person, 13, 10, 20 number of reps of a particular exercise, let us say dumbbell curls. So how do you identify that automatically? The person can actually feel the fatigue and inform us after the fact. But if you are able to predict that fatigue onset in advance, then we can kind of, for example, raise an alarm and inform the person to stop the exercise, or take some rest and move to the next one, and so on. So these are the main areas we are interested in. But there are other areas in which it is possible to apply this analysis and data studies. Others areas like virtual reality, economics, and clothing and textiles industry. So, for example, in virtual reality, I don't know if you are familiar with a company called Leap Motion, where they are looking at human movement, especially through motion sensors, and they get the exact information about the position of the finger joints. And from there, they are able to clearly encode or map the position of the arm, and then they can control an environment based on that. So we are thinking about, can we use biosignals and other data to really augment this kind of analysis and also experience, and then improve the interface. Similarly, in ergonomics and textiles, for example, in ergonomics, ergonomics is an area related to designing workspaces, for example. Let us say you're working on a desktop or a computer where there is a keyboard, there is a mouse, and there are some other devices, right? The position of the monitor, etc. How do you really design these things so that they don't have any long-term, physiological impact on the human? Basically, how you sit, how you move your hand, and how you interact with the computer, everything matters in the long run, especially for regarding your health, your back, your arms, and so on. So, how do we design these devices in a better way so that these things can be mitigated? Same thing can be said about the, especially sports gear. As for example, you just look at these biosignals or any other information related to human movement and try to design these gears such a way that they either maximize the movement or also minimize the amount of obstruction for movement. So these are the possible applications. Now let us look at the general workflow of our research at the lab. So a typical problem, what we usually have is a subject is asked to do a particular human activity, and then we place these sensors on their skin. Basically, skin is the insulation between the muscles and the sensor, right? So we place this scan sensor, this Roxon EMG sensor, and we get the electrical signals about the muscles. And then from these signals, we do some basic pre-processing, and then we can extract features, usually based on signal processing, either in time domain or frequency domain or wavelength domain, and so on. And then we feed these features to a machine learning model. And depending on the problem, we may need further post-processing. For example, if you want to, say, identify the exact location of the particular activity within a longer signal. And then finally, the extracted information can be fed to the next system or next subsystem. For example, so the results, for example, categories or temporal markers of these signals can be fed to the next system, such as the robot. Or information can also be provided to the people like trainers or physicians and so on for further action. So similar workflow is also followed for signal analysis of these biosignals. Again, thinking about strength training. When a person is doing strength training activity, we collect the signals again and we do similar pre-processing. And then we kind of propose a statistical model for the data. For example, say probability density model, for the data and we try to compare it with the other existing models. Once we are sure that a model is accurate description of the data, provides an accurate description of the data, we can extract information from this probabilistic model. One major challenge is what do these parameters from the model mean? For an example, just for a practical example, you can think about experience of a person doing strength training. Is it a beginner? Is it an intermediate person? Or is it an experienced strength trainer or strength training? So we can actually quantify that information through these parameters. So similarly in the sports activity, what is the experience level of a person? Is it a new person or just learning, or is it an experienced or skilled player? Can we quantify those things that are intuitively understood by people, or can we provide an objective matrix, such as a parameter in the model? So these information can be again used by the end users. So that's the general idea. So for today's talk, we will focus on these two particular applications: activities of daily living and strength training, apart from the other areas. So for today, we'll just focus on these two. So let's look at the case study one. In this, we are looking at impact of measurement conditions on classification of regular activities of daily living. So what do you mean by, first let's look at ideal activities of daily living. So by definition, these are the activities that any person or people do in their home or in a workplace, any other place on a regular basis, things like eating, bathing, dressing, and so on. But any other activities where you are actually holding an object, or moving an object, anything of these similar activities can be classified as ADL. And especially those activities which are done on a very regular basis can be defined as regular ADL. That is the focus of this one. Why do we need them? What is the application? As I said before, they can be very useful in terms of assessment in rehabilitation process, or also for when you are able to classify the signals back to the corresponding activity, they can be transferred onto a robot. So that means you can use a robot for rehabilitation. So these are the possible practical applications. So the next question is, how do you quantify these activities? Traditionally, there are many methods. One is to look at the visual information, or you can also look at the positional information, either in first order or second order, or you can also look at surface electromyography. So what is this surface electromyography? So a detailed description of surface electromyography, and what is the neuroscience and what is the sensor science. All these things have been given in the details in the previous version of Wadla. So I think you should be able to find presentations and videos in our case. So for today, we will move on to, once we have the measurements, what are the possible problems that we can actually address? So let us see. So in this particular problem, this is a summary of the literature. So what happened is, in the existing work, people have focused on understanding different kinds of activities of daily living, but the focus is always on particular type of activity or only one particular kind of position. But there were very few studies in which people have looked at both the body position and the arm position, and what is the impact of those combined positions on the, for example, classification of activities. So that is the main focus for us. So if you look at the problem statement, there's a lot of research in EMG. For example, if you search, you will find hundreds of models that can do machine learning and pattern recognition of electromyography signals or any similar signals, which can convert the data into these activities. But the main problem is these data sets are usually built on one single condition. Either a person is probably sitting or standing, but there is no much variation. So here the goal is to look at, comprehensively look at what is the impact of these body positions and arm positions on the performance of this conversion of the signals to the categories. So this is the proposed methodology. So there are 3 body postures and 4 arm positions. That is in total of 12 conditions. So in each of these 12 conditions, a person is performing one of the activities shown here, which are, as you can see, lifting a bottle, pushing a door, pulling a door, and so on. So these are all very regular activities a person performs. So as I said, right, on each of these 12 conditions, you are performing these 8 different activities, and during these activities, each activity is performed around 5 times. So And then during this activity, we collect CNG signals from 5 different locations, as described here. So from brachyradialis, extensor, pollicis longus, and so on. So what is the purpose of that? Because the signal, when you are actually doing a particular activity of daily living, you are not just using one muscle, you are using a group of muscles. So we want to see how is the work distribution or energy distribution is done within each of these muscles. So that it is properly represented and we are able to decode that information to categorize these activities. So once we have the signals and once we do some basic pre-processing, for example, we apply a high-pass filter, that means about 20 Hz, everything is filtered through. And then we remove any line noise. And then we can extract multiple features, which we will describe later. And these features are fed to some of the existing classifiers. And also another recent hybrid deep learning architecture. So, and obviously the goal is to determine the corresponding class. So again, the description of the data set, we have 8 different activities within 12 different combinations of positions and the body and arm positions, and 10 subjects volunteered in this data collection. So for data collection, for any activity where we are involving human beings, clearance from ethics committee of the institution is required. So we have applied for that and we have received the clearance. And one important aspect of our data set is it is completely for Indian population. So obviously because the subjects are all from here. So there are very few such data sets available in the open databases. So our database is extensively available for Indian population. So as I said, these are the activities. And these are the signals corresponding to the activity lifting a bottle. So you can see that there are 5 different channels and then each signal has 3 phases, right? One is the rest, action, and release. So rest means where the person is supposed to not really move his muscles. And then when the computer instructs him to do the activity, it has to basically perform that activity and then come back to the rest position. So there's a transition from again activity or action to next trial. So that's the release part. So we can see those 3 different colors there. So now our goal is to apply feature extraction on these signals. So basically, as we learn in any PR course, you can see that either segment the signals or not segment the signals depending upon the performance. So we extract these temporal features, 16 temporal features, and 9 frequency features, and 5 wavelet-based features. So what we have found is, through this analysis, the fusion or the combination of these features actually gives the best performance. So usually you can fuse results from the classifiers after the fact, after feeding the features to the model. You can also fuse the features beforehand and send the combined feature vector into the classifier. So what we have discovered is this combination of 16 plus 9 plus 5, this full feature vector is able to perform really well. So then to really answer the main question, what is the impact of these different positions on the performance of the classifier? We have done the following experiments. So first one is the all conditions case where you basically ignore the body positions and arm positions, include all the data, and then we divide the data into 70% and 30%. So 70% is for the training and validation, and 30% is for the testing. So we do the basic analysis for this experiment, and then in the next 2 experiments, we look at the impact of these body positions and arm positions. So that means we can train with 1 or more of these positions and test on the remaining body positions. Specifically, in this presentation, we are looking at the situation where we are training with 2 positions, either body positions or 3 arm positions, and testing on 1 condition. So we'll see those results. So this first result depicts the all conditions case. So we have compared different classifiers and we are reporting different metrics. So you can see test accuracy, you can see validation accuracy, precision and recall. So precision and recall are for the test data. So you can clearly see the deep neural network, that means basically a dense neural network with 5 layers, has outperformed the other models that we have compared with. So both in the aggregate condition and also the subject-wise condition, the DNN or the dense neural network or deep neural network has given the best performance. So in other words, when you are not really worried about the conditions and you have access to enough data, the performance is not so bad. But the main issue is what happens when you get a data set or a signal from a new condition. So that's what we are testing here. Let us say these results represent an experiment where, for example, if you see the blue bars, you are looking at the test results of a sit condition, but the model is trained from only signals from stand and walk conditions. Or similarly, when you look at the walk condition, your model is trained for sit and stand, but testing is done on walk. So clearly, when you test on stand with the when you train with sit and walk, the performance is really good. But when you actually train with sit and stand and test on walk, the performance is not so great. In other words, there's an impact of the body position on the classification performance. So similar thing can be said about the subject-wise performance. And one important observation is in this body posture analysis, you can see that CNN by LSTM actually outperforms the DNN network in all the three conditions. And then moving on to the arm positions, again we can see that the DNN has slightly outperformed the CNN by the hybrid architecture CNN by LSTM. So again, we are looking at the arm positions. So clearly the positions P1, P2, P4 are easier to classify. P4 is the best performance. But again, P3, that is the position in which the arm is nearly vertical and parallel to the body. So that position is more difficult to, if you look at the arm positions figure, you clearly see that P3 is different when compared to P1 and P2 and 4, right? So the performance of P3 also in terms of classification is slightly lower. Okay. So to summarize, in both all conditions and arm positions experiments, we can see that DNN outperformed the other models and it gives performance above 90%. But in the body postures experiment, CNN by LSTM, a hybrid architecture, actually outperformed other models. And then the walking condition is difficult to classify in terms of body postures. And the P3, that means the vertical arm position, is difficult to classify in terms of arm positions. So that's the summary of this first case study. And so another issue is this is a preliminary study, so we are currently continuing our work. These are the future plans for this particular problem. So we are looking at understanding the impact of when you try with one condition, testing on only other condition. So one-to-one correspondence in terms of knowledge transfer or low-slow analysis. That means train with a few subjects and test on one subject that was never seen by the model. Leave one subject out analysis. And we are also looking at applying more recent state-of-the-art deep learning models, for example, transformers. And finally, we are also looking at transfer learning in terms of deep learning. So these are possibles. These are the problems that we're currently working on. Okay. So moving on to the case study 2. So any questions before this?
For the previous one, the experiment conduction, so about 10 subjects. How much amount of samples did they have from the 10?
So each activity, each subject is supposed to do 8 activities, right? And each activity is repeated 5 times. Okay. And then they are doing each of these activities in 12 different conditions. So you can multiply all these things.
Yeah, but so considering a population, there is an Indian population.
Correct.
The sample size and statistically, I don't.
Yes, that's a good point.
Population,
getting 10 people. Think about how much time it takes to get data from one person.
Yeah, I understand. No, actually, it was 30. Considering a larger population, I think that 30 people at least will be for the end. For the sample.
I know, there is a magic number for 30 in statistics where people
say because then we can actually put statistically. I think that should be there. Yeah. And with that particular training algorithm, so just wanted to understand what is the CNN algorithms would have been used because since the data set is small, in that how did it was it able to converge really?
Yes, that's what I say. Right, the test accuracy is about 90% in all condition space. Okay, you can see that. I mean, the amount of data required for training is not really a rule. It's more like a thumb rule.
Yeah, I understand that. No, but
and right now we are only looking at training from scratch. But it is possible to do transfer learning, right? Or we use pre-trained networks. That part is not done yet. So we should see some more improvement.
Okay. So does it work same for female and?
Right now, most of the data is from males only. Yeah, we are planning to get data more from females It's also possible. As I said, right, getting one person to sit for 2.5 hours, doing some basic activity and repeating it many times and repeating that in different conditions, 12 different conditions, it's not so easy. Right? How do we convince them? So, but yeah, our teams are working very hard to. And these are not the only data sets. We have 7 different data sets, but they are different aspects. So yeah, we have a lot of data, but yeah, as you said,
Like,
same data we
have
don't
the
have.
benchmarks being done for this in that case? Previously, other benchmarks being done previously.
Benchmark is possible only if they are doing the exact same activity. So I don't think there's any other research papers in which they have done exactly the same set of activities. So yeah, but there are other data sets in which there are different kinds of area. But the only difference is they don't have the same set of conditions, but it's an extensive set of conditions. There are some papers that are shown in the literature review. They are focused only on arm positions. They have ignored the body positions completely. So let me they're probably using only sitting position or only standing position. But whatever, we have all these possibilities. Right? There are number of body positions into number of sitting positions, hand positions. In this case, it's 4 to 3. So there is a lot of variability that is probably providing performance. But as you said, yeah, if we had 30 subjects, but that is also a thumb rule. It's not really like a.
Yeah, because considering this, I see that even the KNN has performed equally well in terms of CNN as well as CMP by LSTM. Looking at the graphs.
Correct.
So how do we even the KNN has in.
Right now, we are not claiming that always walking is going to be difficult. But this is initial result, right? So if we continue taking more data, and this is only Indian population, and that will advantages, we have a good sample of Indian population here because we are in Institute of Information Technology, right? So we have students from everywhere in India. So we have a good sample, but it's not large enough.
Yeah, actually, I'm surprised to see that the KNN has performed better than random forest in this case.
Yeah, it's possible. Yes.
So basically, random forests are bagging.
Yeah. I mean, we expect random forest to perform better. Yeah. So sometimes we observe that KNN does outperform. So anything else?
So in the CNN and biology architecture, like which is what is the feature extractor?
No, yeah, there are many ways you can do that. One thing we can definitely do is feed the original raw signals, the time domain signals, directly to the CNN. For example, in our model, there are 4 CNN layers and 2 binary layers and 2 dense layers. So you can feed you can also try feeding the features directly to the CNN. So it's like having, I mean, it's not exactly true, but it's like having multiple CNN layer. For example, it's just 4 and you feed the features. It is similar to having 7 or 6 layers. But it's not easy to say, okay, whatever features we compute are actually very much same as the CNN features. The CNN features are not easily understood as mathematical features, right? And as mathematical functions. They're more like function approximators. Right? There's an activation function and then we have a non-linear function there. But there is no necessity that there should be a non-linear function. Right? When you say time domain features, for example, mean value, it's not a non-linear function. If it's a variance or any some other feature where there is some non-linear operation, then it is possible it's similar to linear feature coming out of linear. But neural network is always a hierarchical feature extractor, especially if you are doing CNN. So, more layers means more extraction.
Like one of the feature work is like using transformer engines.
Yes, we are working.
Like
We
with
are in fact collaborating with Dr. Rakesh's team. So,
with small data, are you sure like the transformer will perform better
let
than?
us see. The idea is not just use this data. We have a lot of other data sets, not only our data sets. There are data sets called MENA-Pro data sets for this particular EMG sequence. So that is a very extensive. So we can use them for pre-training, and then we can use them. That's it.
Like a small doubt, like if we are having big muscle, then we are getting more signals from.
Now we'll have a demonstration here. You can clearly see that. Yeah, that is definitely true. When you are actually doing strength training kind of activities and your sensor positions are properly done, there is an atlas and the textbook for that. So you follow the guidelines properly. You create in the right place, then you can clearly see the amount of energy is going.
So big muscle is the and most.
Correct.
Otherwise, it means comparing between like if one person is having some great amount of muscle, one person is having small. if both are lifting 5 kgs at a time, like will the signals be same or will
Yeah, in fact, we have done that work. It is not published, that's why we are not able to disclose it. But yeah, we can talk to our PhD student. He will be an expert. He has done that work. We have even submitted a paper on that. So yeah, it is. We have analyzed that problem. There is definitely correlation between the muscle mass and the size of the muscle and the amount of output they can produce. Obviously, right? So,
and you are using five muscles as a signal. You're collecting 5 muscles from
yes, yes. How do we really decide that based on the proximity? So where
can't we reduce the number to 2 or 1? Like
not really possible. Usually in literature, if you see, they usually follow 8 locations. So it can do up to 12. There's no limit actually.
using this, we can use in application like cricket or something else.
Correct, correct.
Like can we do?
No, when you are talking about anything like sports, especially cricket or tennis, multiple muscles are there coordinating the particular action, right? Even for example, bowling. Even though it appears that he is bowling in the right hand, left arm also has a critical role, right? The best bowlers always have the correct position on the left arm. Even for cricket also, when you are playing, your left arm should be the right place with respect to the bat, right? Then only you will get the right ball through right contact. So both the arms should be analyzed. So we have to place electrodes on 3 locations on both arms. Then only we have better understanding. The key point is about coordination. How the muscles are able to produce better coordination so that we have better performance. Because there are many players in which they not produce a lot of strength, but they definitely produce the required output, right? Nowadays, there are more so many cricketers. Not only cricketers, any sports person. It's not really the strength, it's the coordination between the hands. It's not a good very
Thank you.
So, can we move on to the next topic? Thank you. So, in this topic, the main goal is classification and onset estimation of muscle fatigue. It means using surface area, of course, during strength training. So, let us see. So, when you are doing, what is strength training? Just to make sure the definition is clearly understood. We are talking about physical activity, either using weights or just body weights, so that we are able to build our body muscle mass. Okay. And then fatigue is the condition in which you are not able to repeat that training activity. For example, as I said, right, at the beginning, you usually have a limitation depending upon your experience. So 10 trials or 15 trials or 20 trials. So after that, you start feeling the fatigue. Kind of a slight amount of pain, right? Then you want to stop. So, but can we stop it a little bit early? So that means what is the requirement for that? It means can we automatically predict the onset of it? So what is the earliest time before the fatigue actually happens? Can we predict it? That is the question we are trying to see. So that's a not so easy problem. Let us see what are the challenges. So what is the practical application? Again, there are similar applications, right? During rehabilitation, if somebody is going through a therapy, the therapist is actually helping them around, right? So, but if you wait until the person actually feels the pain and then you stop, instead of that, can we automatically know and stop the therapy process? Because that may actually reduce a lot of complications in the future. Similarly, for prosthetics-based training, or when you're using prosthetics in a functional daily life, can it actually predict the fatigue so that you don't stop the activity? Okay? Especially people who are having prosthetic because of the lack of a limb, and they're doing something like running. Right? So if you are able to predict the fatigue in advance, they can stop the process immediately instead of after the fact. Right? So similarly in other areas, sports, when there's an injury, we don't want to really continue, right? But can we do that more automatically? And then aged adults, military and defense applications, so we can use this. We're able to predict it. So again, the summary of the literature review in this area is, again, there are a lot of papers or works in which they have looked at the detection or identifying there is some fatigue, but there is no work which actually precisely identifies the exact time, onset estimation. So at what time the fatigue actually happened? Or in prediction. Prediction is a little bit more difficult, right? Similar problems exist in, for example, in epilepsy prediction. You don't want to wait until epilepsy even actually happens. You want to predict before it happens. These may not be that serious, right? But at least if you are able to predict in advance, it's much more useful. And nobody has really used machine learning in these things. So far, what they have done is they have used some kind of signal processing techniques, define some kind of metric, like you can see here, right? Single spectrum based analysis, such as statistical analysis. They look at some metric and then they decide, like what we study in basic decision theory. We only have one-dimensional signals, and we have a probability density function. We use that to determine the threshold and make a decision, right? Similar to that. And nobody has really studied what is the impact of various conditions. When we are talking about strength training, there are so many conditions. First one is the body weight and the weight they are lifting, and then the experience of the person and the body posture. So, what is the impact of all these things? So, this one we are trying to incorporate those different conditions. So, again, the objective is to look at all these different scenarios and then design a methodology for answer detection and estimation. Okay, and then see what is the impact of all these conditions on these problems. So this is the methodology. Again, details of the. Again, we have this subjects doing these different kinds of activities, as you can see here. 5 different activities. Again, not very complicated, but not so easy, right? Hammer curls, dumbbell kickback, rear front rotations, Jotman curls, and tricep extension. So again, we have 3 different levels of experience. People with no experience, intermediate people, and people who have been doing for 2 years. This is actually a formal definition for these experience levels. So people with no experience obviously know well, and some few months, 1 or 2 months is intermediate. Anybody above 1 year or 2 years, they're considered to be experienced. So we found people like students and other people here in the institute. So we are able to get the clearance for that. Again, we found 11 people. And then again, we do again multiple trials of each activity and all these conditions. So again, it's very challenging, but still available. So, and in this particular data set, we have 7 different locations compared to the previous one. There was 5, right? So you can see the list here. Both the forearm flexor and extensor, and then the biceps, triceps, all the main muscles on the arms. So since we are looking at only the right arm, so we place all these sensors on the right arm. Okay. So once we have the activities and then we get the signals from the 7 channels, then we send the signals through this pre-processing, very much similar to the previous case. And then we label. The main problem here is, since we are designing the problem, so we ask the subjects to really observe their fatigue status. That is, whether they are doing their repetitions, they whenever they feel that they are not able to continue, they are expected to do 2 more reps. So the last 2 reps are fatigue reps, or fatigue curls, or whatever is that. So we clearly know, but in practice, nobody can decide those things, right? So given this training information, you give a signal. Can we predict that? So we basically draw the knowledge that or test trials that the last 2 are actually the fatigue trials. So can we identify them automatically? So that is the problem. So again, instead of using any classical statistical testing method, we tried using machine learning approach. So apply feature extraction and then apply the standard machine learning tools. Then the signal is divided into segments. So the segments are classified as fatigue or non-fatigue. And then we use some, in this case, we started with majority voting. Okay. And then we are able to say this is part of the signal is actually non-fatigue, and then this part of the signal is fatigue. Okay. So let us see the results. So again, the data set, the activities. So these are some of the signals. Clearly, you can observe that there are several repetitions, right? Each repetitions are separated from others. So this activity, these signals correspond to the tricep extension. 7 channels. So obviously, tricep should have the maximum amount of energy. So, and this is the goal. So we have the multiple repetitions, and the last 2 are actually the fatigue. Can we really do that automatically? This is the manual result. We can label them, but can we build a machine learning model that can predict this exact concept? That means the main challenge is not just about classification; it's about the location. So there are multiple issues here. So if you divide the signal into multiple segments and then try to classify, extract features, those features represent the segments, and you classify them. But what is the right size of the segment? Right? And it depends on the activity. Each activity will have a different segment size. Ideally, if the segment is exactly same as the repetition, there is no problem. But the repetitions are of variable size for different activities. So what we do is we take shorter segments, and then later we can stitch them. Right? But the problem is, how do you stitch them? So one possible solution is majority voting. So we'll come back to that. So then to study the experiment, the influence of these different conditions on this performance analysis, again we did a similar experiment analysis with respect to postures, body postures, and then the amount of weight, minimum load, medium load, and maximum load. That is decided based on the actual person's weight and his experience. Okay. If somebody just started where, let us say he's a novice person, we cannot give him like 20 kilo dumbbell, right? So we started with so the maximum weight that a person can lift is dependent upon his experience and his body weight. So that is taken care of. Otherwise, it will not be a proper study. And then the experience, right? So we look at all this. And in terms of onset estimation, once you have the classification result, so we use that, and now we have this time series of temporal sequence of all these segments. So then we classify each of the segments and we stitch them and we apply majority voting. So based on that, whenever we see that there is a strong indication that it is fatigue, we say that is where it starts. But the problem is the error is with the segment length. So the segment length is very high, it is larger. The segment length is too small, then we have better accuracy. But what is the chances of getting it right is there is an issue. Okay. So these are some of the results. The first one is related to influence of body postures. So for example, we train with the standing position and some part of sitting position. What is the performance with the rest of the sitting position? Okay. And similarly, the training with all the data from sitting position, some amount of 30% in standing position, test with the rest of the data. Okay. Or training with stand, test with the sitting data. So all is possible. Inter conditions, intra conditions, and never seen the other condition. You can clearly see again there is some correspondence. And again, the same situation, right? There are only 10 subjects. So it's not a very large data set. But these are the initial observations. There definitely is some impact. And you can clearly see here, when you train with, say, beginner and advanced and test on intermediate people, the intermediate experience, performance is slightly better. Okay. Especially with the basic SVM class. And then if you train with the maximum mid load and test on the minimum load, again the performance is better. I mean, the performance is not drastically better. You can see the x-axis, right? It's from 75 to 100. So there's some 5 to 10% improvement. I mean, difference, not improvement, but difference. So that means these conditions do have an impact. So then the next question is, can we really solidify that? Take more, collect more data, or ask other teams to do more analysis. So these are the possible directions. And the next step, once we have this classification result of each segment, we stitch that, right? And try to predict the exact onset. So you can clearly see one of the examples here. So that is the best, one of the good results. So the error is computed as the time at which we say that the onset of fatigue has actually happened and when it actually happened. So the gap is computed as a percentage of the ratio in the total level. So average error is 12%. So the minimum, the best is 0.43%, so it's very good, but the maximum is 67%. So, and the standard deviation is also 13%, so still there's a lot of work to be done here. Main challenge here is there are no existing methods which can be used off the shelf. We have to develop everything from the scratch. So this is the summary. Weights have an impact, especially minimum load. Small amount of load is easy to classify, and there is definitely impact between different postures. And then experience levels also has an impact, especially intermediate experience is easier to classify. And SVM is generally performing better among the few classifiers that we have compared. So, and then in terms of future work, again, there's a lot of multiple directions possible. One is can use deep learning for this, especially models that are tuned for time series data. And then let us look at, also it's possible to look at what is the impact of different conditions on the deep learning models, right? Especially if you try to do transfer learning. And then another issue with this particular problem is there's a lot of data imbalance. Amount of fatigue signals is very less compared to non-fatigue, right? So right now what we have done is we basically ignored a lot of non-fatigue data. So then there's balance. But that's one technique, right? But there's so many other possible balancing techniques. So we have to look into that. So right now what we have done is undersampling. But there is oversampling possible, or small techniques, and some others. There is a lot of research in that area also. So let us look, it's also possible to look at state-of-the-art balancing techniques and see if there's any impact on it. So that's the things. These are the differences.